In this video, let's show you all the steps in building a neural network, starting from understanding the problem and then manipulating the data according to our needs, then building the architecture of a model, optimizing it, training the model with our data, and finally evaluating it as well. If you don't know what neural networks are, then we have a short video on that one, hence I'm not going to go too deep onto that. Also, you should be having the scikit-learn and TensorFlow modules installed onto your computer. With all that said, let's get into it. Okay, so here is the problem statement, and it says predicting customer churn in a telecom company. Now here, customer churn refers to the rate at which the customers leave the service, and it is a critical concern. To address this issue, a study was conducted on a dataset of 5,000 customers, which basically indicates that we have 5,000 records, and the dataset contains various customer attributes and usage patterns of whether or not they churned. And the insights we see here are we have 5,000 records, and then the attributes are age, monthly subscription cost, contract duration, internet usage, customer services interaction, and more. And then the target variable, the variable that we have to predict, is the churn variable, that is predicting 1 if the customer has churned, or 0 if the customer did not churn, that is, they remained with the service. Now here we have some useful insights which we would generally acquire from data visualization, but in this case they have given it to us. And it says that customers' longer contract durations were less likely to churn, customers who interacted with customer service frequently were more likely to churn, and there is much more, such as higher monthly subscription costs were less likely to churn, and etc. Now what we're going to do here is generally we would import all the modules first and then show you all of the code line by line. But what I'm going to do here is first import the initial modules, and then right as we progress, whenever we need a specific module or a specific function, that is when I will import and show you the actual interpretation. So initially we will need pandas, numpy, and matplotlib. Pandas, numpy, matplotlib.pyplot as PLT. Let's just run the code. Now I'm going to create a data variable and then type in pd.read_csv to load in the dataset. Now here we have a look at the data itself, and we see that we have the age, contract duration, monthly subscriptions, etc. as mentioned in the problem statement itself. And then we also have the churn variable indicating whether the customer has churned or not. Now here, when you look at the entire dataset, we have a wide range of numbers which we will have to standardize or normalize. But then before doing that, I'm also going to use label encoder to change this one, because this is in the format of string values and our machine understands numbers better than strings. So what I notice here is we only have 3 sets of values. One is credit card, one is bank transfer, and one is PayPal. Now what I'm going to do here is use the label encoder function to label each of them to be 1, 2, and 3, or maybe 0, 1, and 2. This is again because our machine understands numbers better than string values. So what I'm going to do is I will import label encoder from scikit-learn. From scikit-learn preprocessing, we import label encoder to do the encoding of numbers, and then I'm also going to import standard scaler to normalize the values, as we have a wide range of numbers over here, like as we see. Let's just run this once again. It's label encoder, and that's good. So what I'm going to do now is first create the label encoder variable by using the label encoder function, like that. Then using the label encoder fit transform function, fit_transform, just like we would do for standard scaler as well, fit transform, and then we pass in the data of payment method. That is the column that we have right around here. Now let's just print the data and see. Data.head 10 records. Now what I'm going to do now is create the label encoder variable and then use the function label encoder that we just imported. And now change the payment method column by using the label encoder fit transform. You would generally do this for standard scaler as well. So fit_transform, and then pass in payment method. Now let's just print the dataset once again to confirm it's working. And as we see over here, we have 1, 0, and 2, which indicates that credit card is 1 and bank transfer is 0, but then PayPal is 2. Nice. Now next I'm going to use the standard scaler function to rescale this to a similar range of values for all the different features. What I will do is first create the scalar variable by using the standard scaler function. But then before that, let me just split x and y. X will be the entire data set minus
the churn variable alone, because that is what we have to predict. So we will have that as our y label, that is the output label. Mention the axis to be 1, and then y will be data churn. Now over here, I didn't mention in place equal to true, because if we give in place equal to true, then this will modify the original data set itself, which actually we don't want to. We're just assigning it to our input label x, but then our output label y will contain data churn. Now I will use the scalar variable that we just created to scale the x values, that is the features in our input label. Scalar dot, again, fit underscore transform, pass an x, and now let's just print our data once again to see. Now next we have to split the data into 80 and 20. Now the reason why we're doing this is we will provide 80% of our entire data to the model to train itself, but then the rest of the 20% will be introduced as a new data to the trained model to see how well it's performing. It's basically evaluating the model. Now what we're going to do is import the train test split function from scikit-learn. scikit-learn dot model selection, import train test split, like that, and we can use this to split our entire dataset into 80 and 20. Now what we're going to do is create 4 new variables: x training set, comma x test set, y training set, comma y test set. And this will be by using the train test split function, and then we pass in x scaled, comma y, and then we also have to mention our test size. In our case, we want the test set to be 20%, so we have to mention 0.2. Now let's just print x train to see if we only have 80% of our data set. Okay, I forgot to run this. Yeah, now this works. Okay, so now it's time for us to build the model itself. Model creation. Now generally in neural networks, you would first create the model's architecture and then use the compile statement to mention the loss function and the optimizer, then use the fit function to actually train the model and then evaluate it. So what we're going to do first is actually create the architecture. Now there's many different types of neural networks models that you can create, but the most famous one, or the most baseline one that you will do almost every single time, is the sequential model, which has to be imported from TensorFlow.Keras. Just type in TensorFlow.Keras.models. As I mentioned, there are many different types of models, and we will be importing the sequential model first. Let's just run this, and over here mention sequential. Now our model is created, but then it's completely empty. We have to give in the architecture, or the number of layers and number of units inside those layers has to be mentioned now. So what I'm going to do is type in model.add, and then inside this we will have to mention the input layer, number of hidden layers, and then the units inside those hidden layers. We also have to mention the activation function and everything. So we will do that one by one. Now again, we have many different types of layers, just like we have many different types of models, but then the one that I'm going to show you in this video will be the dense layer, and now we will have to import that from TensorFlow Keras.layers. So rather than using TensorFlow Keras, I'm just directly going to use Keras.layers, and then I will import dense. Let's just run that. Come over here, and then first, let's create our dense layer. Now this dense layer will have a set number of units which we will mention, and all of those units will perform a specific function and then give us the output of the function, and that output will be provided as an input to our next hidden layer in the neural network. So since this is our first layer, we will also mention the input dimensions as well, but we will first mention the number of units. Let's say we will keep that to 32 units. And then now we will mention the input dimensions. This is basically just giving an insight for the first layer that the initial input that we're going to provide to the model will be of this dimension that we're mentioning right now, which will be xtrain.shape, and then we mention 0. Now we have to mention the activation function, which is ReLU So what basically an activation function is, so after these units perform a specific function and give us the output, it's first passed on to this activation function, and the output is first referred by this activation function. If the output provided by this units is greater than 0, then it will give us the direct output itself. But then if it's a negative number, then this activation function will return 0. Now that will be the input, which will be going on to the next layer, which will be our first hidden layer. Again, I'm just going to type in model.add, another dense layer, mention the units to be, let's say, 16 this time. And now we don't need to mention the input dimensions because this is going to be our second hidden layer. But then the activation function again will be value. Now let's just get to our output layer, that is the final layer. This will only have one unit, that is the predicted unit. And again, let's create the dense layer, mention the units to be 1. But then this time the activation function will be sigmoid, which is basically a function used for classification of 0 and 1. We can also use softmax, but I'm just going to use sigmoid over here, which is segregating 0 and 1. And then now we use the model.compile function. Now what this will do is first take in the loss function. So what loss function is basically indicating the difference between the actual output and the predicted output. And we want this difference to be really, really small. So the loss function that we will be using, the actual function to evaluate the model itself, will be binary cross entropy, because we're doing binary classification using the sigmoid function. When we use the softmax function, we will have to use categorical cross entropy. Now the difference between sigmoid and softmax function is sigmoid is used for just classifying zeros and 1, but then softmax function can be used to classify 10 different numbers starting from 0 to 9. In this case, we're just predicting 0 and 1, so I'm just going to use binary cross entropy. And then I'm also going to mention the optimizer. This is basically the same as gradient descent, but then it has one advantage, which is just it can tweak the learning rates according to the needs. Now, if you don't know what gradient descent is, then you will have to watch the mathematical linear regression video where I explain what gradient descent and many different concepts over there. But for now, what you have to know is this atom optimizer function will help us to reduce this loss function that we have over here to a smaller number. And I'm also going to have metrics to evaluate the model, and that will be accuracy. This will just print the accuracy of our epoch training, which we will get to in a minute. And I'm going to type model.fit to get ready for training the model. Now here we have to pass in the data, which will be the training data, comma the output label, ytrain. And then we also have to mention the epochs as well, which is just indicating how many times should we run through this compile function and get the outputs once again. So I'm just going to make this 10. I will show you once the output is being loaded. And then I will also have to type in validation split, and I will mention this to be 0.2. So what this does is this will again split the data into another 20%, 80% of the training data itself. The reason why we're doing this is we will provide the 80% of our training data to train the model, but then another 20% will be used in the model training process itself to predict how well is it doing on a new data set. Again, you will understand this when we're actually running the code. Let's just run our code and see. We should not be having this to 0. That's my mistake. We should have this to be 1. Now let's just run our code this time and it should work. And our training has started. Now our training is complete, and what we see over here is on the first epoch, we see that the loss function is 0.4, that is we have a loss of 0.4, and the accuracy of the training data is 85%. But then at first the validation loss is around 0.29, but then the validation accuracy is right around 84.25. Now after the atom optimizer has worked its way, we have the second epoch, because we mentioned 50 epochs, so this will be running 50 times, and on the second epoch we see that the loss function has reduced from 0.4 to 0.21 because of the atom optimizer, and we have the accuracy to 90%. Validation loss has also decreased, and we also have validation accuracy of 92%, and this goes up all the way up to epoch 50, where we see that the loss has come down all the way from 0.4 to 0.045, and then we have an accuracy of 98.03. Similarly, for the validation loss, we have 0.089, and the validation accuracy as well is at 97%. Now, what I'm going to do next is use this model to do one more prediction for the test set that we created earlier. Ypred will be model.predict. We pass in the X test dataset, and then we can print this on this. And we see we have different values for each. We can just round this off. np.round. Now run this. So now we're getting zeros and 1 only. Now I'm going to use the confusion matrix to see how well our model is performing on this test data. Now, if you don't know what confusion matrix is, then you will have to watch the shots that I created for confusion matrix. But then you have to know that it's just an indication or a metric used to evaluate the model, which I will show you right now. So what I will do is import the confusion matrix from scikit-learn metrics. Import confusion matrix. We will also import confusion matrix display to have a look at the confusion matrix itself. And then first I will create the confusion matrix variable by using the confusion matrix function that we imported, confusion matrix. And then we pass in the actual values, that is y test, which we already have acquired, and then the y predicted values by the machine, by the model. And then I will create a display variable by using the confusion matrix display. We will pass in the confusion matrix variable that we just created, and then we mention the display labels to be 0 and 1, indicating 0 for the customers who have not churned, and then 1 for the customers who have churned. And the rest will be just using matplotlib functions to first have the fig size. We'll have this to be 8,6. I will plot this with the color, and I'm going to use the cmap function to mention the color, plt.confusionmatrix.reds. This will give us the confusion matrix in red color. plt title, I'm just going to turn on the dark mode to show you the confusion matrix fully. Now let's just run our code. And we see right around here we have the confusion matrix. Here the true label 0, that is the actual customers who haven't churned from the test set, is 854 plus 12, that is 866, out of which our predicted label, the model predicted 854 correctly. And over here the true label 1, that is the customers who have churned in the test set, is 118 plus 16, that is 134, out of which our predicted label, the model prediction, has been 118. This prediction number and this prediction number are correct, and these two are the wrong ones, and we want this to be as minimum as possible. And from what I'm seeing here, this appears to be a good model. Now, to find the accuracy itself, what we have to do is add these two correct predicted values divided by the entire values, that is 854 plus 12 plus 16, 118, and then we will multiply this by 100 to see the actual accuracy. And we see that our model is 97.2% accurate on the test set as well, which is actually really nice.
That was a simple neural network with fairly small architecture. Now, we have an image classification neural network video which builds on many different types of layers with a complex architecture too. You should be watching that since you watched this one. It will be linked if it's released.